IGCSE Computer Science, Syllabus Statement 1.1.2a, represent integers as hexadecimal numbers. So, familiar with the binary system and the decimal system. Binary is base 2, decimal is base 10. So now we're introduced to hexadecimal. Now hexadecimal is base 16. So this means that 16 different values are used to represent each digit in a hexadecimal number. And we also need to know that hexadecimal is closely related to binary. So we're going to look at all of this in this video. In the next video, we'll look at how hexadecimal can be used, why people would use it. Yeah. So 16 different values are used to represent each hexadecimal digit. So what are they? Well, 0 to 9 gives us 10 different values. A to F, using letters now, gives us 6 different values. So if we put them together, we get 0 to F, which gives us 16 different values. So an example of a hexadecimal number would be 2D. To better understand this, here's a table. The decimal number here, hexadecimal number here. So we'll take a look at it. Now, if we go down to 9, you'll notice that they're the same. But then when we go down to 10, well, we can't create another digit to the left. Because if hexadecimal is base 16, it's going to need to have 16 different values for every digit. So that's when we need to start using letters, like A, B, C, D, E, and F. Now, since it is base 16, and only 16 different values can be used for each digit, we can't go above F. We can't go to G. So what we do is when we need to add 1 to the hexadecimal value of F, which is of course the decimal value of 16, then that's when we need to add the left column. That's when we need to increment it by 1, which means that 16 in decimal would be 10 in hexadecimal. And again, we'll look at this when we actually convert decimal and hexadecimal numbers. So how are binary and hexadecimal closely related? Well, binary is base 2, and hexadecimal is base 16. And if you'll notice, 16 is a multiple of 2. 16 is 2 to the power of 4. Therefore, 4 binary digits are equivalent to each hexadecimal digit. And of course, to better understand this, we have a table here. So we have the decimal, hexadecimal, as you've seen previously. And now we have binary. Now, if you'll notice, the lowest hexadecimal digit value that we could have is 0. And that's equivalent to 0 in binary. The highest value of the hexadecimal digit is F. If you notice, is 1111 in binary. Now that's 4 bits filled with 1s. Now this can make it easier, and as you'll see in the next few videos for hexadecimal, we're going to see that perhaps binary could be represented as hexadecimal, and it may be easier for programmers to use hexadecimal rather than binary. GCSE Computer Science, Syllabus Statement 1.1.2b, show understanding of the reasons for choosing hexadecimal to represent numbers. So this is again sort of links to the previous syllabus statement, which is the representation of hexadecimal numbers itself. But this is basically, this statement here talks about why we would actually do that. So this video is quite short because of that. So yeah. So just remind ourselves of this table here, and remind ourselves also that hexadecimal is base 16, decimal is base 10, binary is base 2, and hexadecimal and binary are similar because 16 is a multiple of 2, and 16 equals 2 to the power of 4, so therefore hexadecimal and binary are similar. As you can see, again, 0 in hexadecimal is 0 in binary. F in hexadecimal is 1111. So, therefore, only 4 binary bits are needed to cover each hexadecimal digit, as you can see. So, here's the reason why you would actually want to use hexadecimal to represent binary numbers. And again, we talked about this a bit in the last video, but which would you prefer to read, this binary code or this hexadecimal code? And when we say work with, we mean like to program with. If you're ever like using machine code or assembly or whatever, you might want to decide on that. Actually, assembly is pretty much hexadecimal, but like machine code, like binary. But the thing is, of course, every 4 bits in this equals 1. Well, I'd say every 4 digits in this represents 1 digit in this. So therefore, this is a lot shorter. So probably most people would prefer to read this and work with this, as this can really confuse them. And it's just like this is only like 2 values here, zeros or ones. It can be only those 2 values. So like it can be really confusing and really hard to work with, really hard to find like errors, for example. Whereas here, it's much easier because it's just, again, 1 digit per 4 digits here. So just to recap, programmers would most likely, I'm putting in a most likely because some people might like to read binary, so most likely prefer to read hexadecimal values rather than binary values. And of course, generally because binary values represented as hexadecimal values are shorter, which make them easier to read as well as work with. IGCSE Computer Science, Syllabus Statement 1.1.2c, convert positive hexadecimal integers to and from decimal. So, we've done conversion before with decimal and binary. With hexadecimal, it's sort of the same concept, but it's a little bit different, of course, because we're working with base 16 instead of base 2, so we're going to need to do certain things a bit differently. Now, hexadecimal to decimal is harder than hexadecimal to binary, which we will cover in the next video. So, yeah, let's get to it. So, just remind ourselves of this table, and we have to remember these letters as well, corresponding to the decimal value. So, here we've got a sort of hexadecimal table, basically showing you each column represents a hexadecimal digit. So, yeah, we'll look into that soon, and I'll show you what I mean by all of this. It's sort of like the decimal binary thing we had in the first video, I think, first, probably both, but it'll all make sense. So, hexadecimal to decimal. So let's, for example, convert DE3 to decimal. So the way to do this is to multiply each digit by its value. And again, we have this table here, just like the previous slide. This is what I was talking about. So we can plug in hexadecimal values below these, and then we can multiply them. So remember that D is 13 and E is 14. So we get 256 times 13 plus 16 times 14 plus 1 times 3. So we basically multiply the columns and then sum them up. So we get 3,328 plus 224 plus 3, which makes 3,555. Now, I don't think that the exam is going to give you really large values like DE3. Maybe 2 digits, maybe perhaps 3, but I don't know if they're going to do 4. But because it's a non-calculator test, so I can't imagine anyone asking you to convert really large numbers like that, unless of course they think you're really. All right. So let's take a look at another example. So 2b 3f to decimal. So again, multiply each digit by its value. So it's 4096 times 2, so on. And remember that b is 11 and f is 15. So again, we sum them up, and then we get the value 11,071. So decimal to hexadecimal, well, the way I like to do it, because the other way is a bit tricky, the way I like to do it is to use the division by 16 method. So if we were to convert 200 to hexadecimal, as in the decimal value 200 to hex, so we'd have our table here, and we basically divide the number and then get the remainder of the division. So 200 divided by 16 would give us 12, remainder 8, and 12 divided by 16 would give us 0, remainder 12. So what we do is read the values from bottom to top. So we remember that 12 is C, so it would be C8. It's just like that. Now this is similar to the division by 2 method with binary and decimal, in case you didn't know that. And again, we also read the remainder from bottom to top. And this is the same thing. So let's look at another example. So 3,294 to hexadecimal. So again, set up your table. 3,294 divided by 16 gives us 205, remainder 14. Dividing that would give us 12, remainder 13, as in 205 divided by 16 would give us 12, remainder 13. And then, of course, 12 divided by 16 is 0, remainder 12. We read the values from bottom to top. So remember that 14 is E, 13 is D, and 12 is C. So 3,294 is C, D, E. IGCSE Computer Science Syllabus Statement 1.1.2d, convert positive hexadecimal integers to and from binary. So the last video, we looked at converting hexadecimal to decimal and back, but this video is hexadecimal and binary. Now, this is a bit easier, in case you don't know, or in case you haven't watched the other videos or forgot about them. And the reason is because hexadecimal is base 16, binary is base 2, and 16 is 2 to the power of 4. So therefore, 4 binary digits or bits are required for each hexadecimal digit. And to actually understand what I just said, in case I was being a bit unclear, this is what I mean. So the limit for each hexadecimal digit value is F. So if you were to add 1 to the F, it wouldn't become G, it would become 1, 0. And as you'll notice here, F in hexadecimal is just 4 1 bits in binary. So let's try converting some numbers. So let's say we wanted to convert 3F into binary. So we remember that one hexadecimal digit is 4 binary digits. So 3 represented like this. And of course, it's because like we have 2 plus 1, which makes 3. And for F, remember that F is 15. So it's all of them. Because 8 plus 4 plus 2 plus 1 makes 15, which of course is equal to F. So the answer is 0, 0, 1, 1, 1, 1, 1, 1. And of course you can also ignore the zeros on the left, because it's still it's just for the ease of actually understanding what's going on here. So let's try a bigger number. So E45 to binary. So we have E. Of course, E is 14. 8 plus 4 plus 2 is 14. Let's check that. Yeah, it is 14. 4 is 4. And 5 is 5. Of course, 4 plus 1 makes 5. So therefore, the number is that. I'm not going to read it all, but you get the point, hopefully. If you don't, well. Anyway, let's try some binary to hexadecimal. So let's convert this value into hexadecimal. So we can split it up into sections of 4 digits. And of course, remember that 4 digits is 1 hexadecimal digit. So we get 1010, we plug it in here. We get 1001, we plug it in here. Get 8 plus 2, which gives us 10. And of course, we convert it to A in hexadecimal. Then we have 8 plus 1, which gives us 9. Also 9 in hexadecimal. So our answer is A9. Let's convert a larger value, like this large thing here. So of course plug them in, and then sum them. So 8 plus 4 plus 2 gives us 14, which is E. 8 plus 4 is 12, which gives us C. And 8 plus 4 plus 1 is 13, which gives us D. So therefore our answer is E, C, D. IGCSE Computer Science Syllabus Statement 1.1.2e represent numbers stored in registers and main memory as hexadecimal. So when we say represent numbers stored in registers and main memory, we're referring to binary numbers. So we know that computers read binary values such as this. But humans most likely, again, find it easier to read hexadecimal values rather than binary. So 9b would be the equivalent, the hexadecimal equivalent to this binary value. So when we're looking at registers in main memory, like if a human were to program in a low-level language and wanted to alter this binary number in a register, then they could work in hexadecimal for their ease. So like changing this value to this value, which I can't be bothered to read out because I'm lazy, would be changing 9b to ed. And of course, if you check that, 1110 is E, 1101 is D. So you might get a question on the exam, like an 8-bit register is used to control a washing machine, just like this was actually in the fourth video, this example, the washing machine, when we were looking at the uses of binary. Now we're using it here. But show how only washing machine is on and valve is on will be represented in hexadecimal. So first we look at the binary value of this condition, which would be 10100101, and of course if you plug in the values into this register, it'll be machine on, valve on, and the rest off. So what we do is convert this number to hexadecimal, and that would be A5. Check that. Yeah, it looks, yeah. So again, we can kind of see why programmers would prefer to use hexadecimal rather than binary, but this time in a register. IGCSE Computer Science Syllabus Statement 1.1.2f Identify current uses of hexadecimal numbers in computing. So we've gotten up to the point where we've learned how to convert hexadecimal numbers to and from decimal and binary, and we've also looked at how hexadecimal is easier for programmers to read rather than reading binary. So now we've gotten on to the last statement of this, of hexadecimal, and this is the uses, like the actual uses of it. Like you might already know a few, like HTML, MAC addresses, they all use hexadecimal. So that's basically what we're going to be covering in this video. So let's start with memory dumps. So memory dump is a process in which the contents of a memory are displayed and stored if an application or system crashes. And it's used to help programmers identify and fix the problems which cause the crash. So a memory dump kind of looks like this. So basically, the values here, the contents, and the values here are the locations. So a programmer can look at this and find where an error is. So left values, again, are memory locations, and this makes it easier to actually find where the problem lies. HTML, Hypertext Markup Language, which is what HTML stands for, if you didn't know, is used in development of web pages. Note that this isn't a programming language, but a markup language. And a markup language is used in the processing, definition, and presentation of text. HTML uses these tags, which are used to bracket code. For example, title starts the title of an HTML document, and slash title is used to end it. For example, title hello world title, or slash title rather. So that would title the HTML document. HTML is also used to represent colors on the computer screen. Three primary colors, which are red, green, and blue, are used to represent secondary colors. So you mix them up and they make secondary colors. And the intensity of each of these colors is determined by a hexadecimal value, hashtag RRGGBB. So this is where hexadecimal is sort of tied into HTML. So hashtag FF0000 would be the primary color red, that would be green, that would be blue, and of course you can mix them and give them different intensities, that is hexadecimal values. For example, FF00FF would give this pinkish color, D42460 would give that color, 00C4FF would give that color, 5B9C25, and so on. So here's an example of what an HTML document looks like. So this is one I created last year, and this is Scott's page. And you can kind of see through the tags what these different things do, like what actually happens. So, like for example, body. You can just read the word and know that it's sort of the body of the page. And BG color is of course background color, and it's a hexadecimal value here. And as you can see here, it's 0000FF, which means it's primary blue. And this would be green here. And that would be, well, the title on the page. So H3 is sort of like header 3, and that's kind of a big thing on the top. And this is basically importing an image. Alt is it stands for alternative, and that basically means that if the source can't be found, then the word Scott will be printed instead. MAC, Media Access Control Addresses, basically. It's a unique hexadecimal number which identifies a device on the internet. And it's usually made up of 48 bits, kind of like this, or like this. The 6 N's in the front is the OUI, or the organizationally unique identifier, and the 6 D's is the UAA, or the universally administered address. So basically, the OUI is the vendor number. For example, Apple's vendor number is this, Microsoft's is this. So basically, it's sort of the company number. So like all of, say, Apple's devices, their MAC addresses will start with this, or rather, this. So for example, it would kind of look like this. The UAA is the device's unique serial number, which is set by the manufacturer when it's created. So like in an Apple factory, if you're making an iPhone, that's where it's set. But a user or company can change this into a locally administered address. So this new address will override the original UAA, but it must be unique, which is why doing this is uncommon. So basically they have to be quite careful that it is unique, in case something can go wrong. So why change it into a locally administered address? Well, certain software needs all MAC addresses of devices to be a certain format. It may be required to bypass a MAC address filter on a router or firewall. So basically, if like a firewall has restrictions, as in like it allows only certain allows only a certain type of MAC address, then you'll have to change that into that type in order to bypass it. And also to get past certain network restrictions. So like the MAC address may need to be a certain format to connect to that network. Web addresses. Each character on a keyboard has an ASCII value, or an ASCII. And these codes can be represented using decimal or hexadecimal. So here's a sort of an ASCII table here. So you can see all the characters and their decimal and hexadecimal values. So like D would be 44, and well, capital D that is, and lowercase would be 64, and so on. Some of the characters are here as well, like the special characters. So an example of the use of ASCII is the representation of a web address, or URL. So like Facebook would be this, and percent is used to denote that hexadecimal is being used. So here I have a program which will convert a website that you type in into the hexadecimal form. So if we give this a try on, say, Google, it'll give us this. So we copy that, and you can paste this into your browser and enter. It should take you to Google. So let's try another one. So, like Facebook. We get that. Paste it in. Enter. As you can see, it works. That's pretty much how that works. And our final use is assembly and machine code. So, computer memory can be referred to directly using machine code or an assembly language. So if we take the line in assembly LDA number 12, so basically that means load into accumulator number 12. Well, in machine code hexadecimal, it would look like this. But machine code binary would look like this. So basically, we're going to be learning about assembly and machine code in another topic, but like here we need to focus on the hexadecimal. So basically what this example kind of shows, or it's supposed to show, is how like if we have like, I mean, one line, sure, it's quite small, but like if we have multiple lines of like machine code of binary, that is, like it can be really hard to actually program in machine code. So that's why hexadecimal is usually preferred by programmers to use rather than binary, because like if we have a bunch of zeros and ones, it's gonna be really hard to actually like find, troubleshoot, program, and just etc. all of that. So it's much easier in hexadecimal, and you can sort of easily find errors and just program in general.